In the last lesson, we talked about viscosity. So there was the coefficient of viscosity, just like there's a coefficient of friction. And so today we're going to be talking about how to experimentally measure the viscosity of a fluid. So there are multiple experiments that you could do. And if you do become an engineer or you're going to have to take a class in fluids, they'll probably give you a lab that's based off of this. Connor just woke up. So they give you a lab that's just like this, and they'll ask you to measure the viscosity. So how would you do that? Well, you got to figure out what the terminal velocity is first. So that's when the velocity is moving at a constant speed. Now, you're not going to just drop it in and then figure out what the terminal velocity is. You would have to wait a little bit until it reaches what you think would be terminal velocity, and then you start the time, and you let it drop to some other time right here. And we can say that the terminal velocity experimentally can be measured as the height divided by the time. So this would be the starting height. This would be the time for it to fall. And that would be given the terminal velocity. And then from the last lecture on Wednesday, I showed you what the equation was to figure out what the terminal velocity is. We can rewrite that and say that the coefficient of the viscosity is going to equal, the coefficient of viscosity is going to equal the density of the sphere, which is this object, minus the density of water or liquid, divided by, do I want to write divided by? Yeah, the terminal velocity multiplied by 2 times 9 times g, multiplied by the radius of the sphere squared. So that is the equation that we use to determine the coefficient of viscosity. We know what the density of liquid is. We know what the density of the solid would be. We can measure R. We can measure G. These are all quantities that we can measure, including the terminal velocity. We just solve it this way. And this is how we find the coefficient of viscosity. This is sort of similar, if you remember, to the coffee filter lab that you do in Physics C, where you drop the coffee filter lab and you get its terminal velocity. And then from that, you can figure out some other things. In that case, we find the coefficient of drag, or we try to figure out whether the coefficient is dependent on n or n squared. So this is something similar to that idea there. So this is one way of finding the coefficient of linear drag, or finding the coefficient of viscosity. Here's another way to determine the coefficient of viscosity. What you have is 2 paddles here attached to a rod, and they're allowed to rotate freely. So you've got this apparatus here. You got a pulley, you've got another circular pulley here, and you're going to drop this mass. As the mass drops, as it starts to fall down, this thing is going to rotate, meaning these two are going to rotate, and they're going to experience a resistance. And so if you could figure out how long it takes for this thing to fall and how many times this thing's rotate, you can figure out what the coefficient of viscosity is using this method. Now, there is one more method that you can use to find the coefficient of viscosity. And this one is more of a chemistry thing than it is a physics thing, but I guess you could do it in physics as well. The third method is using what's called a U-tube, not YouTube the channel, but a U-tube, which looks something like this. We've got a tube here, and then this tube goes on to the other side right here, and there'll be a thinner tube right here, like that, and then there'll be another bulb that's not as big, like that. Okay, and so what you do is you fill this tube with whatever fluid that you're interested in. It could be a gas. It's kind of hard to measure with gas, but it's typically a liquid that you fill up to here and here. Okay, so the liquid fills up to all of this gets filled up, and then you're going to have something like this. And what you're going to do is you're going to take a little air pump looking thing, and you're going to pump water upwards like this. So you're going to pump air out, and this fluid is going to start going upwards. So it'll reach some point right here, let's say, which means this one's going to decrease a little bit. Okay, so the fluid's going to go up to that point right there. And what you're going to do is you're going to let go of the air, the pump that was holding all that air in. You're going to release it. And what's going to happen is this fluid is going to go back down again. And what you're going to do is once the fluid reaches this height right here, once it reaches that height right there, you're going to start the time. And once it reaches this height, you're going to end the time. So the fluid's going to start to drain, and you're going to start the time here, and you're going to stop the time once it reaches the end of the bulb. And from that, you could see how hard the fluid is trying to push through this area right here, or this little bubble area. And that also measures viscosity. So they'll have a table that corresponds to the time that the fluid goes from here, and you can calculate what the viscosity is that way as well. So that's the chemistry way of doing it. And this is called a U-tube viscometer. So that's, I've really never used it in physics ever. In fact, I only learned about it trying to prep for this class. So this is probably what they use in chemistry to figure out or in engineering maybe, to figure out the viscosity of the fluid. All right, so you want to measure how long it takes to go from there to there. To do that, let's look at some questions. The first question is going to be pretty straightforward. I want to figure out what the coefficient of friction is, or the coefficient of viscosity is. We have a tube here. We have a falling object. There's your terminal velocity, V terminal, and we got our fluid up there. It's reached terminal velocity, and here's what we know. The height is h, and h is going to equal, did I say 1 meter? Yeah, 1 meter. The height is 1 meter. The density of the sphere is going to equal 8 grams per meter. Is that 8 grams? 8 grams per centimeter cubed. The density of the liquid is going to be 1.2 grams per centimeter cubed. The radius of the sphere is equal to 0.5 centimeters. And finally, the time for this thing to drop is equal to 10 seconds. So if we got that, what is the coefficient of drag? I keep saying coefficient of drag. What is the coefficient of viscosity, mu? In this example right here, you just plug it into the equation that we had written before. That shouldn't be too bad. So let's go back to our equation, which is given by this right here. And all you do is substitute values in and solve. So over here, the coefficient of drag is going to equal 8,000 minus 1,200, because these are in centimeters, and you have to convert it into meters, divided by the terminal velocity. The terminal velocity is just going to be the height divided by the time, and that's equal to 0.1 meter per second. and you multiply it by 2 times 9, or 2 over 9, times 9.8, multiplied by the radius of the sphere, which is 0.005 squared. There. So if you plug those values into your calculator, you will get 3.9 or 3.7 Pascal per second, or Pascal seconds. So 3.7 Pascal seconds is the coefficient of drag here. Now, we always want to compare it to something else. So the fluid's viscosity compared to water. If we compared it to water, water has a Pascal per second of 0.001. So if we compare this to water, it has a viscosity that is 3,700 times the viscosity of water. So whatever this fluid is, it's pretty viscous, maybe like motor oil or something. I don't know. So that's the first question. The second question. The second question is something similar, but we're going to be given different variables here. So we're going to look at the second question. I got to erase some stuff. Okay, for the second question, let's go to this picture first. We're asked to find the terminal speed. We are asked to find the terminal speed, and what we're given is the density of the solid. The density of the solid is going to be 2,715. 2,715 kilograms per meter cubed. And the density of the liquid, we'll say, is glycerin, and that's equal to 1,261 kilograms meters cubed. And is there anything else? The radius of our object is 2 millimeters. And the coefficient of the fluid is going to be 1.2 Pascal seconds. So 1,200 times the density of water. We have that, and we want to know what the terminal speed is. How are we going to do that? We use our equation V terminal. We just have to rewrite the equation I had before, which I probably erased. Good on me. So V terminal is going to equal the density of the solid minus the density of the liquid divided by the coefficient of viscosity times 2 over 9 multiplied by G multiplied by R squared. And that'll give you the viscosity of the terminal velocity. So you'll just plug everything into here, and you get 2,715 minus 1,261 divided by 1.2 multiplied by 2.9 multiplied by 9.8 multiplied by 2 millimeters, which is 0.002 squared. And so the terminal velocity from this, V terminal, is going to be not very fast at all. So it's going to be 0.0106 meters per second. So it's not moving really fast. This is a pretty good solid here, and it's not moving fast at all. Okay, so that's the second question there, but we're not finished with this second question here. let's make it more interesting. Now that we have the terminal velocity, what I want to know is the acceleration when you've reached half of the terminal velocity. So we know that as this thing falls, it's going to accelerate until it reaches terminal velocity. So what's the acceleration when you are at half of the terminal speed? My papers are about to fall there. That's okay. So we want to know the acceleration when the velocity is equal to half the terminal speed. So what would the acceleration be there? Well, you got to draw your free body diagram and look at all the forces that are acting on it first. So you have the force of gravity pointing down. This object is falling down, so there's going to be a buoyant force going upwards. There's also going to be a force opposing this thing from falling down, which is Stokes Law, and that's given by the drag force. And so if we do the sum of forces here, we would have the drag force minus the force due to the buoyancy plus the buoyancy force minus the force due to gravity equals mass of the object times the acceleration of the object. And what can we do from there? We can rewrite some of this. So this is given by Stokes Law, which is 6 pi let's see. I'll actually call down to be positive. Let's call down to be the positive acceleration. So we'll make this negative, and this negative, and this positive. So this will be negative 6 times pi times mu, which we know, times RV. R times the velocity of your object minus the buoyant force, which is going to be the mass of the liquid displaced times gravity, plus the mass of the solid times gravity. And all of that is going to equal the mass of the solid times gravity, because it's the solid that's falling down there. So that's what we have there. What can we do next? Well, we have an equation for density. We know that density is equal to the mass over the volume, which is going to equal the mass over 4/3 pi r cubed. And the density of the solid and the volume of the solid and the volume of the displaced water is the same. It's going to be given by 4/3 pi r cubed. So we can rewrite this equation. Let's write it some more. It's going to be minus 6 times pi times mu r times v minus the density of the liquid times 4/3 pi big R cubed. So that's mass times gravity plus the density of the solid 4/3 pi big R cubed times G. So that is the mass of the solid times gravity, and all of that is equal to rho solid. What did I go wrong here? Right there. That should be acceleration. Okay, so mass solid times acceleration. So 4/3 pi r cubed times a. So this is just from the sum of forces equation. And we want to know what the velocity is at terminal velocity here. So I'm going to replace this thing, v, with v terminal divided by 2. All right? So I'm going to replace that with v terminal divided by 2, and I'm going to take this side and divide it all over. And we will get that the acceleration is going to equal, let's clean it up a little bit nicer. So I'll bring this to the front here. You've got 4/3 pi r squared, or cubed, sorry, times g. That can get factored out from here and here. I'm going to multiply it by the density of the solid minus the density of the liquid. So that's these two terms, minus 6 times pi times mu times r times v. And it's the velocity of the terminal velocity divided by 2. Because we're asking for the velocity when it's the terminal velocity by 2. And all of that is going to be divided by this term right here, which is the density of the solid 4/3 pi big R cubed. Okay, and we have all of those values over here. We know what the terminal velocity is, we know what the coefficient is, we know what the radius is, and we know those two densities. So you just substitute all that into there, and we get the acceleration at V terminal divided by 2 is going to equal 2.61 meters per second squared. So that's what the acceleration will be halfway. And when it's full terminal velocity, the acceleration is going to equal 0. Let's see here. And so when the velocity is 0, what's the acceleration going to be? When you first drop it, the velocity term would go to 0 here, and the acceleration would be this over that. So in the beginning, the acceleration is going to be equal to, well, this term here, and this term cancels out. So it's going to be the density of the solid minus the density of the liquid multiplied by g divided by the density of the solid. Can I write that somewhere? Let's write that over here. When time is equal to 0, so acceleration at t equals 0 would equal the density of the solid minus the density of the liquid divided by the density of the solid. So this is a constant, it's got unitless, and you multiply it by g. So it'll be this multiplied by g will give you the acceleration right at the beginning. And it's not going to be 9.8 because you've got the buoyant force that's still there. Okay, so that's that. The last question is a very interesting one. It takes the same idea that we've talked about here, except we're going to add to it. Now, I'm sure some of you have been in swimming pools before, and there's that one person that always farts in the swimming pool, and they create a little air bubble, and that air bubble goes up. So that's what we're going to be looking at here. We're going to be looking at a person that farts in a pool, and the air bubble that's going up because of it. So here is our pool. And in the pool, we have an air bubble. So this is an empty pocket of air. And we want to know what the terminal speed is. Okay, from this air bubble, and I'll call it air bubble. So what do we need to know to solve for this? Let's write down our givens here. The givens, this is water here. The givens are going to be that the radius of the fart bubble, the air bubble, is equal to 1 millimeter. The viscosity coefficient is going to be given by 0.15 Pascal seconds. The density of the liquid is given by 900 kilograms per meter cubed. Okay, so that's all of our knowns, and we want to know what the terminal speed is going to be in this situation. So in order to find the terminal speed, you need to draw your free body diagram. In this case, there are going to be two forces acting on it, An air bubble, for all intents and purposes, has like zero weight to it. It's going to be going up. So here, the only two forces that are going to act on it are the buoyant force, which is pushing it upwards. This is the buoyant force. And you have the drag force, which opposes the motion of it, the force due to drag. And if we want terminal speed, these two forces have to equal the same. So the sum of forces has to equal 0, which means that the drag force has to equal the buoyant force. And so the drag force is given to us by 6 pi mu r v terminal, not just any v. I can't set this equation equal to each other unless I call it v terminal. And the buoyant force is given to us by the mass of the liquid that's displaced times the gravity of that. And we can write that in terms of density. So it would be the density of the liquid multiplied by the volume of the liquid, which would be 4/3 pi r cubed multiplied by g. Okay, so we have this is equal to that right there. And from here, we can get an equation for the terminal velocity. The terminal velocity is going to equal rho L times G times the what is it called? The volume, 4/3 pi big R cubed multiplied by G, all divided by whatever's left over here, which is 6 pi mu times R. And so that is the coefficient, this is the terminal velocity for an air bubble. And you can plug all these numbers into our equation here, and we will get that the terminal velocity is going to equal 0.0131 meters per second. So it's not moving really fast. But that's how you find the terminal velocity for an air bubble that's going up a cylinder. Okay, so that's it for today. Next time we'll talk about shear and stress with fluids. So I will see you in the next lesson, which is going to be on Friday. Thursday, there is no lesson. Wednesday, there is no lesson. I have to give a test for my other class. So Friday is when the next lesson will be. Until then, adios.